So I'm going to give an example for a little unusual case study for this conference. And it talks a little bit about how to use the power of big data and big data analytics to bring about breakthroughs for diseases, in this case, ALS. So what is ALS? ALS, amyotrophic lateral sclerosis, or Lou Gehrig disease, is a neurodegenerative disease that affects the nerve cells activating the muscles. And as the nerve cells activating the muscles die, the muscles are unable to be activated. So we see progressive paralysis, eventually leading to death relatively fast, within 3 to 5 years. So the disease is 100% fatal, and it's very rapid. And you can see here an example of a patient. It's our CEO, Shai, and you could see that he transformed from being an Ironman athlete into a fully paralyzed ALS patient within about 3 years, which is a pretty typical path for an ALS patient. And I already said that Shai, who's a patient, is our CEO. So a little bit about us. We're a nonprofit called Prize for Life, or Pras L'Chaim in Hebrew. We were founded by another ALS patient, Avi Kramer, who you could see here. Avi was diagnosed with ALS when he was 29. He was a Harvard Business School student. And he decided to really take all of his experience and skills and network from Harvard Business School and take that into the field of accelerating a treatment for ALS. And the model in which he decided to do that was the PRIZE model. So the idea was to understand all of the reasoning of why there isn't a treatment for ALS right now, understand all the barriers, and around each one of these barriers, to develop a prize program for whoever will remove this barrier in the way of a cure. Now, there are many barriers for developing treatment for ALS and for other diseases. And what I want to talk about today is the type of barriers that relate to data and that relates to big data. So ALS is a rare disease. It affects about 1 in 1,000 patients. And worse than that, because it affects the patient so dramatically and the death rate from it is so rapid, at any given moment there aren't a lot of patients. So in Israel, that has about 8 million people, there are about 800 patients. So one of the greatest barriers for understanding and developing treatment for ALS is scarcity of data. There isn't a lot of data. A large ALS clinic only sees a few hundred patients. So it's very hard to accumulate the amount of data needed to really have a very thorough understanding and development of models for ALS. Now, so on our side, we want to understand how so we see that there are different types of data being developed. There are better technological advances in gathering data, collecting data, better data, cheaper data, all sorts of different types of data, genetic data, clinical data. And we wanted to understand how we could bring all of this advancement into the field of ALS. So we want better data sources, more research on these data sources, more collaboration on the data. And we want to we wanted to know how could we do it? So how could a small patient-based organization promote such a change? And I'm going to give you 2 examples, 2 case studies, with regard to how can even a small organization make a change in the amount of research being done on ALS. The first case study is just getting enough data on ALS together. And the problem is that there isn't a lot of data available to bring together. And we had to identify new sources for data. And the source that we identified was looking at past ALS clinical trials. So ALS doesn't have a treatment right now, but it did have a lot of clinical trials testing a treatment, all of which had failed. In the last 25 years, there were approximately 30 clinical trials testing different treatments. All of those have failed. But we thought that maybe in these trials, despite their failure, there can be meaningful information about the patients that can improve the planning of a next clinical trial and improve the success rate in this field. So we approached drug companies and asked them to donate the data from past completed ALS clinical trials, and we would bring them together into a database. And we created the database called the Pooled Resource Open Access Clinical Trial Database, or the PROACT database. It's available, open access, for researchers worldwide. Of course, I would be very happy if any one of you had looked at it. It's available at www.alsdatabase.org. So we took all this data, and we brought it together, homogenized it, and brought it into a database, and opened it up to the research community. This was in December 2012. And the type of data that we see in the PROACT database is the type of data that you see in clinical trials. So it's about 8,500 patients right now from 17 completed trials. We are in the process of gathering more data, so there would be there would be 23 trials and over 10,000 patients within a few months. And the type of data that you see is the type of data that you see in ALS clinical trial, which is very standard, basic clinical data. So you have demographic data, you have family history, so other diseases that you see in the family. You have the clinical information from the neurologist visit. You have standard lab tests, standard tests of vital signs such as pulse and heart rate and blood pressure. And you have all this clinical information. What you don't have is any other information. So you don't have genetic information or other biological information. You have the type of information that is immediately accessible for patients. And the benefit of that is that anything that you find on this data is immediately accessible to patients. It's something that you could take and put in an ALS clinic tomorrow and use it for the patient benefits. And we were very lucky, and I'm going to talk about why in my case study, but we were very lucky and see a lot of work happening on the PROACT database. So since it was launched 2.5 years ago, it's been requested by over 450 researchers worldwide, including drug companies, universities, and informatic companies, like a lot of the people here in the room, some working in collaboration with pharmaceutical companies, some working on their own project, demonstrating the efficacy of different algorithms, and so on. And I think that within itself comes to show that just by making a large amount of unified data available open access, you can already incentivize new research and new sort of results that were not available before in ALS. And I don't have a lot of time to go over what type of research, so I just outlined it more generally. So the type of things that you can find include, for example, you could look at disease pathways and identify novel biomarkers, to looking at other diseases, comorbidities, to looking at the blood test of the patients. You could try to understand the natural history of the disease and the heterogeneity between the patients. You could look for more from a clinical development perspective, from developing better clinical trials. So you could simulate how a clinical trial should be. You could try to simulate what would be the disease progression, what would be the reaction to medication for different patients. And to say it the most broadly, one of the biggest benefits is the things that are not listed here, but everyone would come up with. So the biggest benefit is really growing the quantitative workforce that is exposed to ALS, that has looked at ALS data and has done work with ALS. Because we believe that through bringing new people into this field and bringing new ideas, new algorithms, fresh new minds, already we would come up with many other things that are not listed here, but would be tremendously important for ALS. Now I'm going to move to our other example, our other case study. So we try to actively encourage people to look at the data and bring them into this field. And the way we usually do these things is through a prize program. So we developed a prize, the ALS Prediction Prize. The prize was ran in summer 2012, so before the database was available open access. And we did it with collaboration with a bioinformatic team, the DREAM project. And we planned it the following way. So we ask participants, data scientists, bioinformaticians, mathematicians, computer scientists from all over the world, take 3 months of patient data and tell us how the patient would look like 9 months from now at the end of the year. So model the patient prediction over the coming 9 months. This challenge was ran with a price of $25,000. It were later increased to $50,000 because we received another donation. And to sort of go over it a little bit more, we gave the participants a subset of the PROACT database, about 1,800 patients, but we didn't give them all of it. We gave them a training set to develop their model on, and they could test it within the challenge, and the results were appeared on a leaderboard. But then, when the challenge lasted 3 months, when the challenge was over, we asked them to submit the code, and we ran the code on a separate validation set that they've never seen before. And we looked at the results and compare the predictions of the prediction that they made for ALS progression versus the true progression of the patient. And we compared it using root mean square of deviation and correlation. So basic measures of difference between predicted and true numbers. And one thing that we saw that we were already very happy about, even before we saw the results, was the interest of the community or the data community in this challenge. So we had over 1,000 participants from 64 countries. And when we surveyed them, we discovered many very interesting things. First of all, we asked them, what did you know about ALS before you joined this challenge? And how much did you know, rank your knowledge about ALS from 1 to 5? And 80% of them ranked 1. So they had 0 knowledge about ALS. And we were able to bring completely new mind into the field of ALS. The second thing was, what made you decide to work on this challenge? And the majority of the solvers didn't do it for the $25,000 prize. They may have heard about it because of the prize, but they said that they would have also have done it for free. And a lot of them have expressed explicitly that had they known that their algorithm has value for something as important as ALS research, they would have been very happy to use their knowledge even for free, because a lot of them didn't feel that what they do in their daily life is as important as creating solutions for ALS. So we're already very happy that we made this first connection between data scientists and ALS research. Now to the results. So we actually end up dividing the prize between 2 winning teams. One of the winning teams came from academia, and it was a professor at Stanford. The other winning team came from industry and was from a marketing analysis company in Washington, D.C. that focuses on understanding marketing and pricing strategies over the online marketing. And their results were comparable, so we just divided the prize between them. But just to give a realistic flavor of what were the results. So I think a lot of people here talk in terms of root mean square of deviation or correlation. And it was already said here before that root mean square of deviation is not a good measure of actual impact. So what was the actual impact of the results? First of all, we tried to see what would be the impact on developing new treatments for ALS and testing them in clinical trials. So when you plan a clinical trial, usually before you even start it, you need to plan the size of the trial, and you do that with regard to what you assume is the variance within your population. So how many patients do you need in order to see an effect beyond the natural variance of the population? And if you have an algorithm that predicts ALS progression and that reduces the variance by somewhat, what would be the effect of this on the number of patients that you need for an ALS clinical trial? And so we did that in collaboration with a drug company and asked them to incorporate the algorithm into the simulation of a clinical trial as they would do it in planning of a clinical trial. And the answer was that using the algorithms, was able to reduce the number of patients needed for a clinical trial by 23%. So for a large ALS clinical trial, it would be about 1,000 patients. So it reduced it to less than 800. So 200 patients less are needed, or 230. And we tried to give an economical estimate. So what is the meaning of 230 patients less? Of course, you cannot give an exact estimate because every company plans their clinical trials differently. But if you just focus on the money that it takes for the 230 patients to be taken to a doctor, examined by the doctor, and taken back to their house, so just this minimal cost per patient, the algorithm was able to reduce the cost of a clinical trial by about $6 million. So this was a $50,000 challenge that produced results. They're able to reduce the cost of clinical trials by millions of dollars for each future clinical trial. And I think the reason for that it really worked on a completely virgin territory. There were no other algorithms, so the improvement was so dramatic. The second thing that we wanted to see is, can it help ALS patients in the clinic? And for that, we compared the performance of the algorithms with performance of clinicians. So we devised out of the entire PROACT database, we took 14 representative cases. We gave them to 12 ALS clinicians from all over the world, and we asked them if they can predict the progression of ALS for these patients, the same way we did it in the challenge. So we gave them 3 months of data, and we asked them to predict how the patient would look like a year from now. And then we gave the same 14 cases to the algorithms and saw how the algorithms predict. And you can see it in the chart on the right. So the chart is a little complex because we have 2 measurements. The x-axis is correlation. So for correlation, you want the higher the score, the better it is. So you want scores that are on the higher or the right side of the chart. And the y-axis is root mean square of deviation, which you want as close as possible to 0. So lower is better. So there's a little arrow there that shows what is the better type of results with low RMSD and high correlation. And you could see that the 2 algorithms, the 2 winning algorithms, outperformed all of the clinicians. I can say they didn't only outperform all of the clinicians on the 14 cases, they outperformed them on each individual case. There were no case in which a clinician predicted for a patient better than the algorithm. And the reason for that is the clinicians really don't have any tools right now, or didn't have any tool before now, to predict how the algorithms are going, how the patient are going to predict. And then this showed us that the algorithms can have meaningful value when used in the clinic with the clinician, and can give them important tools to improve their clinical care of the patients. The last thing that we wanted with regard to real-life value was, so we have these algorithms and they predicted ALS progression. What were the features that were most predictive? So we looked at the 20 most predictive features. Some of them were known from the literature or obvious, but the algorithms were also able to identify 4 features that were never reported before in the literature, and you can see them here. Some of them are very surprising and maybe could shed very interesting light on ALS research, for example, blood pressure and pulse. And the lower 2, which is phosphorus and creatinine, which are 2 standard blood tests, are now being tested prospectively in patients to see if they could be biomarkers for the disease, if they could tell us something meaningful about why different patients progress differently. So this really opened also new paths of research for patients. So now the challenge was over, and we had the 2 winning algorithms. And we wrote a paper, and we put the algorithms available as supplementary material, so everyone can download them. But the question was, what now? So how will these algorithms make it to clinics, make it to clinical trials? And we were actually very lucky, because one of the 2 winning team, the team from the marketing analysis company, decided to take it upon themselves. And they used the prize as seed funding to open a startup company that further developed the algorithms. And because they understood the importance of these algorithms for ALS patients, they decided to develop the following model. They're developing these algorithms as service for drug companies per pay, but they're also developing these algorithms for clinics for free, as a donation of their time. And the algorithms are now already being used by 3 drug companies and 12 clinics. Sadly, all of them in North America, but this is within less than 3 years from the end of the challenge. So we really do see that it made it all the way to patients. Now, we wanted to go beyond what was predicted in the ALS prediction prize. First, we have more data. Second of all, the prediction prize asked for one model for all the patients, and we know that the patients are very different. So our next step was to devise another challenge, and this challenge is going to be launched this summer, and the reason I'm talking here is really hoping that all of you would be interested in being part of the next challenge that should be launched in June next month, June 2015. And we'll go beyond the prediction prize and ask not only what would be a good predictive model for the entire ALS population, but can you stratify the ALS population into meaningful subgroups of ALS patients and say why will one patient progress very slowly and one patient progress very fast? So just to give the range, a very fast patient would be someone like Lou Gehrig, who gave the disease its name in the United States, who was a young baseball player, and so was definitely very healthy before he had ALS. Yet he succumbed to the disease within less than 2 years. And on the opposite side, we have someone like Stephen Hawking in the UK that has been living successfully with ALS for the last 52 years, making him the longest living ALS patient. So what is it that Stephen Hawking has that Lou Gehrig didn't have? And if we were able to stratify them meaningfully early on in their disease, we would be able maybe to understand how we could make Lou Gehrig into a Stephen Hawking. So my final message is really for you, how can you be part of this journey to making all of the ALS patients into a longer lasting ALS patients? Thank you.